Hi, it's Terry Dennery of the MathWorks. So anyways, in this video, I'm going to fix this. You can kind of see that slow rotation. I was able to track down that bug. But mostly what we're going to do is just kind of put in the vehicle measurements, kind of what's its altitude, what's its essentially three-dimensional position, which for right now we'll express in a XYZ according to a reference coordinate frame, the world reference coordinate frame, right? And we'll do a little bit more on the measurement, including kind of orientation as well as velocity and angular velocity. Okay. All right, so tracking it down, there's a little bit of a fatal error I made here. Let me just hit Control U. We'll get in there. And then we need to do that too. So that prop direction needs to be accounted for both the feed forward piece as well as kind of setting the angular velocity command. All right. And so again, we'll just kind of reuse that here. All right, so that's got the proper parameterization. And then again, we want to be consistent with the other two instances of this controller. So these two will be a 1. There you go. All right, so no longer are we getting that kind of drifted rotation. And at 10 seconds, it takes off. All right, and in a way, that's part of the point. That I know it's 10 seconds because I commanded it to, and I believe my controls are good enough that that will happen. And that all that command really takes place right here, right? And so the trajectory of movement will, let's see, it'll launch at 10 seconds, it'll take 100 seconds, and let's see, wow, I've even kind of hard-coded it. Yeah, I need to fix this at some point. But I think if we dived in there, we'd see that I've set it to go to 2,000 meters, which it does. And we'll see that in a moment too. All right. So anyways, but this is kind of the point of this video is, well, how do we know? Right. And there's a little bit of diving into this model. It's really kind of in the mechanics of what I want to get access to essentially this right here. I believe that if we double click on here, well, actually, we could argue, this is the center of mass of what I'm calling the chassis. So why don't we be very precise and we'll kind of begin here. And so I'm going to just take one of these frames and instead of calling it CS4, I'll just call it chassis CM. Okay. And one of my tricks is I always just copy the external port. That's what those hexagonal shapes are called. And I just keep on reusing it as I go back up. All right, and I'll paste it right there. And we'll continue to go up, and I see it right there. And I guess that looks pretty good. All right, so we got essentially access to that coordinate frame now, and so now let's just make the measurement. Pop that out. All right, and so this is going to be a frames and transform thing. And it's essentially this guy, the transform sensor, but also that world reference that I was talking about. And so this is essentially setting the XYZ. It's consistent. Oops, not in here. It's in this model a little bit, but it's consistent with the world reference we've been using all along. Okay. Anyways, I want to do this, right? And now I want to just kind of throw this into a subsystem because we're going to do a little bit with this. So create a subsystem. Clip it. Call it vehicle. CM. And it's in here that we choose everything we want to measure, right? And so I like rotation sequence. It's essentially an Euler angle thing. And my favorite is going to be XYZ. So it means, this is about rotation with Euler angles. You rotate about X, that's going to set a new Y and Z direction. And so your next one will be about that new Y orientation, and then finally the new Z. Okay. Anyways, if you've done a lot with Euler angles, you probably know what I'm talking about. Anyways, let's measure angular velocity. Translation. So this is really going to be the position measurement. And then let's get the translational velocity. And there we go. We got a lot of stuff now, right? And so we need to kind of space this out so we can kind of see those signals. All right. We go up. I want to kind of fix something here too. Is that I want this to show up on the left side. And when I go like that, that's going to look pretty good. And we're going to basically have an output signal come out on the right. Anyways, we'll get to that in a second. All right, so the big kind of thing about SimScape is that SimScape's a physical calculation and units are super important, and it's like if you're using force, you better know it as opposed to using newtons or whatever. And in general, I like to work in the metric system, and so I'll do mostly metric, and as well as radians, I usually prefer over degrees. So anyways, there's a number of reasons that we introduce this block. So it's a PS to simulate converter. And I'll click it on this right here. And this is where I put in a unit. And so, well, I guess I'll call that radians. Okay. And now it's come down here. Angular velocity will be radians per second. Okay, so the next three are going to have that unit, so let's just copy it. I'm sorry, the next two. Okay, and here's where I like to introduce a mux block, because I think of one of my buddies teaches mechanical engineering. He's always says, be careful when you call something a vector. Just having three components doesn't necessarily make it a vector. And there's all kinds of stuff he talks about with regard to unit basis and stuff like that. So anyways, my phrasing, I'm generally a little cautious to call this necessarily a vector, but certainly it's a good vehicle to express a vector. And so this is the mux block. And I'll put in an output right there. Actually, we're not going to do that output, but quite yet. We're going to actually go for a bus output. So let's do the next one, which is position. And for the output unit, go for meters. Take one of these muxes. I didn't get that. There you go. Okay. And then finally, we'll do velocity, which will be meters per second. All right, good. So we got the measurements. And so we will set this up with a bus, and so I'm going to just call it M bus. Again, I might change the name later, but basically I want to just remind myself this is a measurement. And so let's get a bus creator. Let's make it pretty big. All right, and we'll drag that in like that in like that in like that, and there you go. And it can be a little bit of a pain to get all this stuff right. I'm just going to leave it. Probably fix it in between videos. It's nice to have nice horizontal lines, and really this is kind of not set up so that they're naturally coming out with that. The bottom three are, but anyways, let's just go ahead and call it what we want to call it. And so I'm going to call this Euler XYZ. And that's the sequence. This I'll just call, let's use real language, angular velocity. Position, and I'll call this translational velocity. Okay. Double click on the bus, and that all seems like it worked pretty well. And so we have that as a measurement coming out of here now. All right. And so let's get our bus selector. We'll select position, which we know is a three-component vector, and so we'll use the selector to pick off the first element right there. Right. And so let's put in a scope. And let's see if we get up to 2,000 meters. Now, notice this is only running right now for 25 seconds, and we know that this trajectory has been set to start at 10 and run for 100, so let's run it for at least 120 seconds. And well, that didn't work. I don't think it did. Yeah, so let's see what I did wrong. Oh, rookie mistake. Z is the third component. Okay, so let's run it one more time. And we reached 2,000 meters. And I'll just kind of see how close we really are. We're pretty close. Okay, and I'll justify that a little bit, but I want to do that kind of last move that I did on a previous video, which is that you always need to employ feedback, and you're never going to have perfect information. And so these local kind of, well, local, maybe not the perfect word, but let me just say that these measurements of things like altitude are possible, and we got great instrumentation to do such things. So why not use it? And I'll still advocate the better you understand your system and the environment that you are going to operate it in, you'll be surprised how well you can achieve what you want it to do, right? And that this idea that well, in a way, you never understand your system perfectly, and you certainly aren't going to understand the environment in which it can operate, and certainly rainstorms and heavy winds and all kinds of things can occur that just are not anticipated. Well, that's why you have feedback, and feedback just gets that. I'll call it that, instead of local, let's call it that immediate measurement, and that you employ that as part of your overall strategy. And so this thing that we've been almost referring to as a trajectory planner, Well, what it's going to really do is evolve into the flight control system. And what we're still doing is we're just kind of going up and in a vertical position. You know, that's that kind of what I call it symmetry of all four essentially propeller units are doing the same thing. Well, as we begin to kind of have it move where we want it to be, we're going to start essentially differentiating each of those propellers, and that the flight control is going to evolve in its sophistication as it employs feedback, but as well in the mission to kind of not treat these units as the same thing and to differentiate among them. And we'll see quite a bit more calculations going to take place in this component right there. So anyways, thank you.